All right, so for those of us joining on YouTube, we just went into breakout rooms. We talked a little bit about the COVID-19 data as people were filtering in, and now we're going to go think about Hamiltonian paths and cycles. So we're working through page 70 in our notes here. It starts with some proofs, with the proof of the path cycle principle, and move on from there.
I can pick it up and like get it if you guys want.
Okay.
Actually, where do you go to get it again? How do you get the screen thing? Share screen?
It should be at the bottom of the bottom of your screen.
I'm clicking it, but it won't work. Oh,
I can do it.
okay, yeah, you want.
Want the whiteboard or?
Do you want to just get the? Do you have the like the packet up or no?
I can have it in a minute.
All right.
Give me
I
one
just
second.
think that'll be easier to look at that.
I might be able to have it in a minute.
Okay, wait. Let me just try to. Let me see if mine will share now. Oh yeah. Okay, wait. I got it.
Okay.
Do you see that?
Yep.
Yes.
Okay. Okay, so we're starting at some proofs.
Yes.
There, yeah.
All right.
Did you get a chance to read this first part yet?
I didn't.
Yeah.
I would.
So Jane, you've thought about this a little bit, right?
Just a little bit.
All right, so I'm gonna go float around to the other rooms while you all get settled.
Okay.
So do you see this degree sequence down here? Sorry.
Yeah.
So since there's 1, 2, 3, 4, 5, 6, 7 points, you divide it by 2. So for the first 3 points, they all have to be greater. So like 2 has to be greater than 1, which it is. 3 has to be greater than 2, which it is. 3 has to be greater than 3, which it's equal to, so it's not. So there's no Hamiltonian path.
Okay. I get you.
Cycle.
Right.
Cycle. Yeah.
All right. That's good. Well, that was on the homework, so that's definitely clears that confusion.
Good to know.
All right. Well, I
And
guess we
then-
can keep going with this.
So then the next one is saying, oh God, I gotta like remember it all. So if there is a Hamiltonian cycle, you can only, you can add an edge to try to make it more clear, but only if the number of degrees of the vertices add up to the number of vertices, I think.
No, that's the other one. That's Banish Fatal. That's down the bottom.
Oh, what's this one?
So this one says if you have a Hamiltonian path, okay. So if you have a Hamiltonian path like this one right here, okay.
Yeah.
And the degrees of the endpoints are big enough. So they're saying, so this is the degree, this is this condition right here.
Yeah.
So if there's a path and the endpoints have high enough degree, then you can extend to a cycle somehow.
Okay.
Okay. So you don't, this isn't the one where you add any edges.
That's the next one.
That's the next one, yeah.
So that's that one, Matt.
Kind of looks like a face. All
And
right.
then the Banish-Fatal is the thing I was just saying. So do you use the the Bonnie-Chatel thing and the like the degree sequence thing, do those pretty much just always go hand in hand?
No. So it just depends. So all these are different tools that you could use at different times. So depending on what kind of information you have, then you're going to use different tools, right? So
Yeah.
if you're studying a graph and you can quickly find a Hamiltonian path, then
Then you would
maybe
use
the path
the
cycle
path.
principle is something you want,
Okay.
right? And so if you have a lot of vertices with high degree, then maybe this Bonnie-Chatel condition is something that you want to.
Because this one feels like kind of useless without. What's the one with the degree sequence?
POSA.
I don't know why. It feels like those two are only really very useful when put together.
Well, the POSA condition kind of says, if you look around your graph, the place that you're going to be limited are the vertices that have really small degree. Okay, so if you have a vertex of degree 2, you don't really have many options at that vertex, right? You kind of have to use those two edges that are going out, and it puts a restriction on you. And so POSA is saying, hey, if you look at your vertices of small degree, right, your smallest degree vertices, if they're big enough, then everything is okay, right? So you're not going to have too many restrictions on you. So it kind of gives some illumination into what's happening in the background in these graphs, which is the restrictions when you're trying to find these Hamiltonian cycles is, hey, the vertices of small degree are important, right? So that's sort of one thing to take away from POSA's conditions is, anytime you have that small degree, less options, which means, it's higher importance. The high degree vertices, tons of options to get to and from that vertex, so maybe it's less important, right?
And so if they don't necessarily pass that test, where like the degrees are too small, that doesn't mean there isn't a Hamiltonian cycle. That just means we can't prove that there is one, right?
Correct.
Okay.
Yep. So it's not an if and only if. It's only a right.
Yep.
So just same thing with Bonnie-Chatel. There's a then here. Okay. So.
Okay. Let's go do some of the questions.
Sounds good to me.
Yeah, so what we're going to do is that path cycle principle, we're going to do is try to figure out if we have a Hamiltonian path, how do we prove that we can find a Hamiltonian cycle? Okay, so we're going to list our vertices out. So A is going to be our starting point, B is your ending point, and you're just going to label the vertices along the way with, what step they are. So the first step away from A is V1, second step away from A is V2.
So is it, oh yeah, okay, never mind. Sorry.
Okay, so what we're assuming here is that A and B have really high degree. And so by really high, we mean when we add them together, you get more than the number of vertices. Or at least the number of vertices. Okay. And so what we want to do is there's going to be some sort of connectivity stuff that's happening down in here, right? So A is going to be connected to a bunch of stuff, and B is going to be connected to a bunch of stuff. We don't know where it is. And so what we're going to try to do is inside of these red edges, we're going to try to pick some of them where we can then go and use them, make a swap in here, swap out an edge for two edges among the red so that there is a Hamiltonian cycle. Okay, so that's going to be a little bit more clear if you go down to the next picture, right? So what I want you to do is spend some time thinking about this and saying, if we can find a certain thing, which is going to be described here, try to guarantee that you have that Hamiltonian cycle, right? So try to find it inside of these conditions.
Okay.
Okay? All right.
Sweet.
So isn't it just saying that if A is connected to a vertex, then B is going to be connected to the adjacent one,
Yeah.
right?
To one adjacent one, back, I
Mhm.
guess. Yeah.
Yeah.
Okay.
Welcome to our room.
Hello.
Hey.
So Yes, what you all said was exactly right from what I heard.
Cool.
So Sam, we talked about this a little bit on Tuesday, right? So you taking
Yeah.
the lead here?
Yeah. It's just I'm still a little bit foggy on the restrictions on I, but like I kind of understand because it's like if I were 0, for example, right, then that would mean that like A would have to be adjacent to this one again, kind
No,
of.
no, no. So
Doesn't
Okay.
I mean that is I the number of the degree of the vertice? Sorry, that was
so I is the index in the list.
okay. So it has nothing to do with that.
I is like, so I is going to be 1, 2. It's going to be, so how many steps away from A is it, right? That's going to be your I.
Okay.
So let's think about this, right? So let's say I was equal to n minus 2. Okay, so right now we want it to be at most n minus 3. Well, let's bump that up by 1. Okay.
Mhm.
So that would mean that B is adjacent to n minus 2. Okay, so this is so B V sub n minus 2 is an edge, and then A and one more than this, right? So the one after it, V sub n minus 1 would be our edge. Okay, so V n minus 2 is right here. So what is V n minus 1?
It's B.
B, right? So if you picked I to be n minus 2, A would have to be adjacent to B. And then we
Oh.
said, yeah, that could happen, but if it does, we don't care, because just take that edge and then you have a cycle. So,
Yeah.
so what we're saying is we're placing this restriction here to say, okay, we want to make sure that A is not
All
adjacent.
right.
We're assuming A is not adjacent.
Okay. That makes
Does that
sense.
make a little bit more sense?
Okay.
Yeah.
Yeah. Okay, so then I think that I'm pretty solid on this chunk then after that. How about
Okay.
you guys?
I'm just confused how that like guarantees that you'll have a Hamilton cycle. Do you know what I mean? Like being in those restrictions. Is that what it's?
Yeah. So Sam, can you find? Do you remember that the cycle is in this picture?
Yeah, in the
Yeah, I get
Yeah.
where the cycle is. Like it's all the way. It's like a figure 8. Okay.
Yeah.
All right.
So right, we would have all of these edges, right? So what we know that all of these edges are here.
Okay.
We know that all of these edges are here,
Mhm.
and we know that this edge is here.
Mhm.
Okay? So I could travel through every single vertex and get to B, but I can't get back to A. So instead, what you do is instead of starting out this way, we're gonna sort of jump halfway down, because we know that this edge is there somewhere. Then we're gonna go up, and we're gonna come back down, and then we're gonna go back up this way.
Okay.
Right. So we're swapping this one edge for these two.
Okay.
And so all the other edges are the same. So what will be helpful, I think, is down here in G23, you can find there's an actual graph here in this G23 where you can try this with actual vertices and an example that doesn't have dots in it.
Okay.
Okay.
Yep.
All right. Gonna keep flowing.
To list all of the vertices that are
Hi
adjacent.
again.
Hello.
Hello. Each subject on the vertices. Okay, so now we're just listing all the vertices.
Yeah, so
Okay.
I'll write them out real quick. So all the vertices that are adjacent to A except for V1. So
Here, should we erase this?
subtract 1 from the subscript, vertices in your list, and then it's equal to S. Okay.
We have
Uh,
V2.
So V2 is connected. and you're subtracting 1. V3,
Mm-hmm.
subtracting 1.
And V5.
5, subtracting 1.
And that's it.
So that would be new V1, new V2, and new V4. Right?
Yep. Did you write that? Oh, there you go. It's right there.
Okay.
Yeah, the text is weird. You gotta hit like enter before it.
Yeah.
Okay. All right, so now list all the vertices adjacent to B.
All right. And that one's going to be called T, right?
Yeah.
So that's V4, V3, and V1.
Mm-hmm. And then,
Oops.
so yeah, then that's just T.
And significance.
So what do you all notice?
That they both have V1 and V4.
And so why did you care about V1 and V4?
It's connected to both A and B.
So that is
V1 is.
true, but V4 is not connected to A.
Yeah.
Um,
I don't know.
So when we come up here, you get to annotate. So you're interested in this VI, right? So if you can pick out this VI, so you're saying you want B to be adjacent to something that comes before one of the neighbors of A.
mm-hmm.
And so, like, what was subtracting? You subtracted 1 from all these. What was all that about?
Find the previous vertex.
Yeah, so what you did is you went through and you said, hey, we're gonna find all of the neighbors of A. We're gonna find all the neighbors of A, which is like this.
Yeah.
And then I'm gonna subtract 1 from that. So I'm gonna take a step back. And when I take a step back, I'm looking at this. So this one, it goes into S.
Okay.
Okay.
Right. So we said we looked at everything that came before something that was a neighbor of A. And then you said, then you looked at the neighborhood of B. So anything that was adjacent to B. And that's exactly what you want to find, right? You want to find a vertex that comes before something that's adjacent to A and is also adjacent to B.
Okay.
Okay.
So these are all the predecessors to things that are adjacent to A.
Mm-hmm.
And then these are all the things that are adjacent to B. And those are precisely the 2 things you need to be this candidate here, this VI.
Okay.
Okay. So what it's telling you is you could go ahead and you could you could choose, you actually have two options here. So you could have I be V1, which means what we're going to do is we'll start at A and we'll go out to the next one, follow our Hamiltonian path around to B, we'll come back to V1 and then finish it off, right? So that is one Hamiltonian path where you chose V1.
Mhm.
And then you also have an option to say I could choose V4 as my option, where so we're going to go from A out to one more than V4. We're going to go A out to V5, follow our Hamiltonian path around to B,
Yeah.
jump back to V4, and then follow it all the way around.
Yeah, that's the cycle we got when we first looked at it.
Yeah. So that's the one that's by choosing V4. And then you had another option, which was V1. Okay. So in this case, you actually have plenty of options, right? You have two ways that you could complete this. You don't need two, you only need one,
Mm-hmm.
right? So you only need one option. So what we want to do is we're going to try to guarantee that if I look at these sets, that they have to overlap. Their intersection can't be empty. Okay, so if you could guarantee that, right? So if you can look at these sets and you can guarantee that they're not empty, then you're done. Right? So the proof is going to be, hey, yeah, we can extend to a Hamiltonian cycle because we're going to go from A out to V I plus 1, go around, jump back to VI, and come back around like this. Okay, and so all you have to do now is prove that these two sets are, the intersection's not empty.
Oh, that's cool.
Okay?
Mm-hmm.
All right, so keep going. I'm going to continue to float around.
All right.
Or 1, 2.
Connect to make the cycle.
So I think that's giving you the point that so A connects to V minus 1 and B connects to V.
Right. V6.
Well, this time it would be V4. Like V4 is the connector between A and B. So we know there's a path between A and B. And according to, I forget which rule it is, POSA or something like that, there should be a Hamiltonian path. And I think this tells us what the connecting value between A and B are, because if there is a cycle, then A and B need to be connected somewhere.
The only thing I'm uncertain about is up above. It's saying that the vertex that's connecting to A is VI plus 1, and then it has like B as just V1 VI.
Is it for me?
But
Oh.
I thought if V4 is the
VI plus 1.
yeah. So that's like kind of what I'm. But that's not connected to B. That's connected to A. That's what I'm like questioning. Oh, I guess B is.
Well, so I guess A or B could be either one. Like this is
Oh,
labeled
okay.
A, but it could just be, you could just change the labels and make it B.
Okay.
Is that right?
Yeah, I mean, I guess you could go the other way in the path if you wanted to, sure. But we'll keep with A as the starting point and B as the ending point. So you did put a Hamiltonian cycle on this graph in G23, but it isn't the one that I was thinking about.
Well, so there's that one, and then there's the one. So we figured out. So does this mean that V4 is the connecting point? Like B should go to V4, and then A goes to V3.
No, A doesn't go
No?
to V3. So think about the graph above. So you're right that so what you're going to say is I is equal to 4. Okay.
Okay.
So B is connected to VI, so that's going to be V4. But then A is going to be connected to I plus 1, and this is going to be V5.
V5.
Yeah.
Right? So A should be connected to V5.
Okay.
Yeah, that's what I was trying to say because I feel like if
There you go. That
Yeah.
makes sense. And then do I just like connect them up and make it work?
You're going to go like this.
So I just make a fish. Yeah.
Yeah, like the blue I had in there.
Nah, perfect.
Okay, but now you have more options too, right? So you didn't have to choose I is equal to 4. You could have chosen I is equal to 1, right? So you could have chosen V1. So this would be 1, and then this would be 2, right? So A would go out to V2, like this, and B would go out to V1. So those would be your two edges. And then your path, you'd go A to 2, all the way around like this to B. You take that edge, and then you come back to A like that.
Just make a different fish.
Yeah, right. So it's always gonna be in this figure 8 pattern. The theorem does not say that that's the only option, right? So there's tons of, like you illustrated yourself when I came in here, that there's tons of different Hamiltonian cycles that you could have picked, but this will always work, right? So you're finding the case that works regardless of what graph you're dealing with, right? So the proof is that this type of figure 8 or fish structure, like you're saying, will always work out.
Sweet.
Okay, so yeah, Matt, your concerns were good. I was going to have the same comments.
All right, cool.
Boy.
All right.
And then,
We're up to now 25.
Well, we got this to read. So it
Cool.
says, now we return to the general proof using this diagram. And then remember, we have to show it.
this and P for some I values.
So what your goal here is to show that these sets S and T, when you look at their intersection, it's not empty. Okay, so you want to make sure that if you can show that in every case, when you take the intersection of S and T, if it's not empty, there is one of these choices for I, and then you can do the fish or figure 8, whatever thing to extend to Hamiltonian cyclic.
Well, so for the, I can't remember what it's called, for the Posa one or something, it said the number of vertices has to be greater than 3, right?
That's right. So if you only have 2 vertices, there's no way that you're going to have a cycle.
Okay, so we'll just, okay, yeah. Sweet.
All right, so you all feel pretty good about things?
Yeah.
So wouldn't the set just be this on the left side? This right here?
Yeah, so what he was just saying pretty much was saying the intersection wouldn't be empty, and that's the intersection for S and T would be V4. So yeah, that's what he's talking
Before
about.
V1.
Oh yeah, V1 too. I didn't see that.
Okay, I see.
So we just need to make sure that S and T have at least one shared value.
Yeah, but you want to, the first thing you're going to do is you need to tell me more precisely what S and T are. Okay, so that's what's going on here. You gotta come up with a rigorous way to say what S is and a rigorous way to say what T is.
Okay.
Okay.
Well, actually, so let's look back at that diagram. See what? So
All right, I'm gonna keep moving here.
All right.
yes, there's the
Sticks out to me as being like kind of like an odd man out.
Yeah.
Yeah.
Hello.
Hello. Just trying to get up here. What you're thinking about.
So we're discussing the importance of these sets here.
Mm-hmm. Yeah. So what do you care about? Like, you have V3 circled.
Yeah.
So when I look at those two sets, V3 is of no interest to me whatsoever.
Yeah. I kind of was circling it, saying that it was like specifically like the odd man out, like because V3 like was never like 3 was never an I value, and
I did use it as an I value. I just looked at my screenshots. I used it with V3 and V1.
You can't do V3 V1. They have
Can't
to
do
be
V3 and V1.
No, they have to be consecutive.
Like V2 and V3 or V3 and V4
Oh, okay.
as-
Wait.
for this kind of situation. Are we looking
Oh,
at the
sorry.
fact
Yeah, it's
that-
V2 and V1. So yeah.
Are we
Yeah,
looking
so-
at the fact that V1 and V4 are same in both of them?
Yeah.
And
Mm-hmm.
So what they're saying is you can choose I to be equal to 1, or you can choose I to be equal to
Oh,
4. Those are your
Okay.
choices.
oh,
I see that.
Okay.
But then why are these
Yeah,
other
so-
two in here?
that's
So if you choose I to be 1, what that means is B is adjacent to V1 and A is adjacent to V2. Okay, so you'd have, remember that X that was in the general diagram?
Yeah.
So that when I is 1, that's the X that you get right here. And then your Hamiltonian cycle is you're going to go from A to VI plus 1. You're going to follow all the way around to B. Then you're going to go back down this edge and you're going to come back up to A.
Mm-hmm.
So we get this. Now, so that was, oops, let's back up here. So that was I equal 1. So let me do a different color. When I is 4, right, you're going to have this and this as VI plus 1. So you're going to come down this edge, and then this is going to be the X in your diagram. And so you would come down A to V5, you'd go up this way, down to V4, and then all the way back around. Right, so when you pick I equal to 4, you get the same kind of structure. So there's two different options for you to pick in this case. And so when you look at this, what you're trying to do is you're trying to show that you have this choice for I, which means the two sets that you just defined here, S and T, have to be non-empty.
Oh,
Or sorry, their intersection has to be non-empty.
I see. Okay, that makes sense. To me, at least.
Ramon, Kirsten, what do you think?
Yeah.
makes complete sense.
So that's going to be, so for the rest of this, our whole goal is to show that, hey, when we look at this set S and we look at this set T, we're going to try to put a rigorous definition on them. And then we're going to also show that when we look at their intersection, there's something that's definitely there.
Okay,
Okay.
I see.
Yeah.
So as you
Makes
scroll
sense.
down, right? So I don't know who's controlling.
Yeah, I'm just working on it. Here we go.
Yeah, so let
I'll
me,
get rid of this crap too.
yeah, okay.
Sweet.
Yeah. So yeah, if you scroll down a little bit more, this
Yeah.
S and T, we're going to define them rigorously, and then 26, 27, 28, 29, our goal there is to show that the intersection is not empty.
Okay.
Okay?
Cool.
All right. So so far so good here?
Yep.
Yeah.
All right. I'm gonna keep moving fast here.
All right.
This is 3, back to 1.
That edge isn't there? I don't really know. We're really
So I think I know what you're saying, but I'm going to say it differently.
okay.
Scroll up just ever so slightly, please. All right. So say this is our VI, this one right there.
Mm-hmm.
Or yeah, say that's our VI, and we have to go to the one that's, was it right after it or right before it?
Right before it.
Oh, okay. Then say that it's this one, that's our VI. If we go to the one that's right before it, then we already know that they're connected to B or A or whatever. Then if we come over to A,
You're going the wrong way.
I am?
Yeah.
Okay.
So the I, so when you're talking about the I value, the two vertices that you pick are I and then the next one in the list.
Oh, okay.
Okay, so it would be like if you picked 2, if I was 2, then it would be 2 and 3. If I was 3, then it would be 3 and 4. If I was 4, then it would be 4 and 5.
All right.
Now, and you can't pick I to be n minus 2.
Yes.
Is that what you're asking here? Why can't you pick it to be n minus 2?
Yeah, and I was trying to explain it, but like you said, I was going the wrong direction.
So there were some good ideas there. So let's assume I is equal to n minus 2. Okay. And then that would mean I plus 1 is B.
Mm-hmm.
Right? So that would be I and I plus 1. But which one is A adjacent to I, or is A adjacent to I plus 1?
I plus 1.
I plus 1. Okay. So this is I plus 1. Okay. So what if A was adjacent to I plus 1?
Can there be a cycle?
Yeah. And then we already excluded that case, right? So way back early on, we said if A was adjacent to B, this isn't really that hard to do. Just pick the edge. So we're assuming, right? So through all of this, we're assuming that A is not adjacent to B. And so if you could pick I to be n minus 2, necessarily A would have to be adjacent to B, which is what we're not considering here. And so that's why we have this n minus 3 condition.
Oh.
Makes sense.
Okay. So for 25, we didn't really know what it was asking. We know that like the intersection of S and T can't be equal to the empty set.
Yep.
But we didn't really know what it wanted us to put in the brackets, because we had that, and then we had that VI minus 1 is within T, right? Because we wanted
Here's what I would say for T.
Oh, so then A is adjacent to VI plus 1?
Yeah.
Oh. Okay. So it's just kind of what is already stated from above. Like
Yeah, but I think the author wanted you to really think about it, make it precise, you know.
Okay.
So Marcus is the author, so Dan Marcus. So he said in this, he gave you this thing of like, oh, look at all the neighbors of VI and then subtract 1 from the index.
Mm-hmm.
And it was like, that's sort of like a weird way to say it. And so I would say down here, I would say that exactly what you said, Sam.
Okay.
A is adjacent to V sub I plus I plus 1. I don't. I typed I plus 1. I don't. Yeah. Anyways, here V sub I plus 1.
Okay.
Yeah. Yeah, and then you want to show that they're non-empty. Yeah, exactly right.
Okay. That makes more sense.
Clear my stuff out of here. So did you give any thought to why that might be?
Well, I mean, I feel like well, because when we're doing, so S is the vertices that are adjacent to A but minus 1. So then you have the VI plus 1. I don't know why, but that makes sense that it would be plus 1 because you're subtracting 1 in the set. But I don't really know why.
All right, so 26, 27, 28 are going to walk you through this. Now, the thing is, we're just going to think about the sizes of the sets, okay? So you're going to think about what are the number of possibilities that could be in these sets, and then how big they have to be. Okay, so remember, you're drawing from the same pool of numbers, 1 up to n minus 3. Okay, so you have n minus 3 things that you can draw from. And then each of them is going to have to draw some number. Okay, and so what you're going to be thinking about is so two people are picking numbers from the same pool of numbers, and you're going to have to say, oh, we're gonna select so many things that two people will have to select the same one.
Okay.
So sometimes we call this pigeonhole principle.
Okay.
If you remember that. All right. So if you have n plus 1 pigeons and they all go into n holes, then 2 pigeons have to be in the same hole.
Mm-hmm.
Right. So that's going to be the idea that's going to pop out of this.
That's like the vertex you'd start at, because then you could get back to it.
Yeah. Right. So that would be, there has to be something in both of these sets.
Okay, that makes sense.
Right. So think through this 26, 27, 28 is what you're going to be, is what's going to work through that.
Okay.
Okay. I'm going to keep floating here. So I may not make it back to you. I said 145. So probably I'm going to visit each of these other groups, and then I'll bring us all back together to.
Okay.
Okay.
All right. See you in a bit.
See ya.
Yeah.
Yes.
Sure. I started some of it, so.
Yeah. So, G27.
I'm reading what you got here. G27.
So we
We just got over discussing that. You know what I mean?
Yeah.
So all I such that 1 is greater than or equal to I is greater than or equal to n minus 3, and it needs to have the correct amount of degrees. Like there's a certain amount of degrees that A has, but we're ignoring the first one that it's adjacent to. So it's the number of degrees it has minus 1. And then the same thing for B, but for B,
Yeah.
right?
So those little like fill in the blanks for S and T, those are the fill in the blanks for us.
Can you do me a favor? Can you make sure that Noah goes to put this fucking thing in the wash?
Oops, somebody moved the screen.
Yeah.
I was gonna put the definitions for the S and T in there.
I think Edwin has control and he's like talking to someone, I think, right? I'm like,
I see.
he's walking
Oh,
away.
there he goes.
Okay. Anyway, so the S set is adjacent to VI plus 1, and then B is adjacent to VI. So that would be your S and T. And then you are all thinking about, yeah, we're moving those over. So I'm a little bit confused as to where we are here.
Edwin, can you scroll back up to G26-ish? I think we accidentally scrolled down a little bit.
Yeah, right there.
Sweet.
Okay, so yeah, so this. Hey, how did you move that text?
I think only Edwin can do it.
Oh, okay, all right. Yeah, so that should be, Edwin, that should go over, the A should go over next to the S, yeah, the B, yeah, there you go. Okay, Edwin has to do it, all right. Gotcha.
Oh, okay.
Yeah. Okay.
Not bad.
So you're thinking about this one, G27?
Well, just for G25 real quick, wouldn't that make the S and the T set only 1 each?
No, it's every vertex that's adjacent to going to select. And every vertex that's adjacent to B, you're going to select.
Okay.
Okay. Okay, so think about this, right? So if you were to play a game, and so in this set of integers 1 through 19, so Matt, you're going to select 10 numbers, and Eric, you're going to select 10 numbers, and how do you know that the two of you have to select something that's the same?
Because there's not 20 separate numbers for us to
Yeah, right.
pick
And
different
so
ones.
Right. So if you picked, right, so if you picked 8, right, so Eric, if you picked 8 and Edwin, you picked 11,
Right.
right, so there's 8 and 11. Do you have to pick the same numbers?
No.
If there's no,
There's
what do you,
3 other possibilities. Oh.
Right.
Like, you have to
With
pick
8 and 11, you could each
19
pick your own because there's 19 things, right? But if somebody had to pick 2 and somebody had to pick 18, there has to be an overlap because there's not 20 distinct things for you all to pick. There's only 19 of them.
Okay, I get what you're saying.
And so this is going to be the same idea for, well, we're going to try to generalize this, right? So if you look at the set S, how many things does S have in it?
3? V1 before?
either 1 or I n minus 3 things.
No. It depends on A.
It's one less than the degree of A.
That's right. And then how many things are in T?
1 less than degree of B?
Yeah.
No, just the degree of B.
Well, no, because you're not. Remember in the previous one?
Oh,
where
yeah,
you're
okay.
Yeah, except for B6 there, so I think it's the same thing.
All right, so we're picking degree of A minus 1 and then the degree of B minus 1. Okay, so this is going to be the number of things that lives in S, and this is the number of things that lives in T.
Right.
And what's the total number of things that you have to choose from?
N minus 2, when N is like the number of degrees of A and plus B.
The degrees of A plus the degrees of B, or?
Well, it's that plus minus 2.
Is it?
Also, the degrees of A plus the degrees of B minus 2?
There might be repeats though, right? So like you wouldn't count, like if they both
Well,
have.
if there's repeats, we're great, right? We want there to be repeats.
Right. But that means you wouldn't count that repeat twice.
Right.
There's one. There's.
So we don't
Oh,
care
the
about
N-
repeats though, right? So
Is it N divided by 2? Is that how many?
nope.
No. All right.
So what you said over here, right? So this would be like your degree of A minus 1. And this over here would be like your degree of B minus 1.
Okay.
And then this number right here, this is your N minus 3. Does that make more sense?
Yeah.
Okay, so let's see if we can put all this together. So we got about 10 minutes left. I'm gonna go ahead and I'm gonna leave you all here to think about this, but we're gonna bring it back and we'll put a cap on all this. All right. So I'm gonna check in with the last group, and then here in a minute or two, I'm gonna close the rooms and then we'll come back together.
Okay.
Okay.
Before the edge is added. Assuming that G prime contains a Hamilton cycle, we have to show that G also contains a Hamilton cycle. This is done by contradiction. Suppose that G does not contain a Hamilton cycle. We will show that this
You're
is
reading it to us now?
I don't know.
Yeah.
I just started reading it. No one stopped me.
No? I like it when things are read out loud.
Right?
How did we?
Yeah, no.
I make
How did we do on the previous group? Did we make sense out of it? Did we get there?
Yeah. After turning it over for a few minutes, I think we all understand it.
Okay. All right, so I'm gonna bring us all back together. We're gonna close out the breakout rooms, and we'll see. So some of the other groups are not. They haven't put it all together yet. So
Okay.
maybe you all can give us some insight there.
Oh yeah.
Okay, so I'm gonna close this out, and then we'll go back to the main session. All right.
Perfect.
All right.
All right. Bye, guys.
All right. Welcome. So you all, other people are going to be coming in too here soon. They'll close. The breakout rooms are all going to close. But do you all feel comfortable sort of giving us some insight? You're all muted, by the way. So if you want to talk, you have to unmute. So I have. All right. So is everybody back in with us? We have everybody. Yep, everybody's back. Okay, so we were gonna make some sense out of this proof. Did we all get there in the other group? So I was just in breakout room 3. So we feel comfortable with this. So where I left off with some groups was this one right here, G28. Does anybody wanna walk us through that? Any volunteers?
I can.
All right. So tell us about it, and then as you're talking, what I'll do is I'll like write on this and try to mark it up and stuff.
Okay. So in number 26, we said that the number of elements in S is d of a minus 1, and that's because you're taking the degree of that vertex, and then you're excluding the connection between A and V1, so it makes it minus 1. And then the same thing applies for T, but it's D of B instead. And then, so if you're trying to find the total number of elements in S plus T, then you can just say that it should be, you just add those two together.
Okay, so you got something like this, right?
Yeah. And then that gives you that D of A plus D of B minus 2 would be the total number of elements. And then we basically want to show that D of A plus D of B is the same as the total number of elements. I mean, the total number of vertices,
Mm-hmm.
right?
So you want to show that D of A plus D of B is how big?
Is equal to the number of vertices.
Is it n minus 2?
Is equal to n, Kirsten?
Yeah.
Okay, if that were true, right? If it was equal to n, this would be okay. So it's not necessarily equal to n, but it is
Greater than or
right. And so how do we know this? How do we know that the degree of A plus the degree of B is at least n?
I don't know. I kind of forgot that part.
Okay, so
I just kind of knew that it was, and I just.
Okay, so we do know that that's true. So that's our assumption, right? So the statement of this theorem says if you have a Hamiltonian path and the degrees of the endpoints are large enough, meaning they're at least n, right? So that is one of our assumptions in the statement of the theorem. All right, so we do have that this is true. Okay, so let me clear some of this out. So we know that the number of I did not want to do that. Oh my gosh. Okay. So we're gonna erase some of this stuff here that we wrote on. So we know that there's enough stuff here. So can anybody? So Kirsten did a great job walking us through that. Can anybody finish it off? What have we actually proved here? Crickets. All of you.
I'm gonna just guess something. So are we saying that if it's possible that then the amount of vertices that it would take is n-2 to create a Hamiltonian cycle?
No.
Sounded good.
Okay. So we're gonna take so if we let's back it up here. Okay. So S and T, right? These are gonna be, if something is in those two sets, that's our candidate for I. Right. So if we go back, right? Remember that we had this picture and then we have this I, right? We wanted to know what is a candidate for that I. And the candidates had to be in S and they had to be in T. Remember that? So we want to make sure that, hey, we're going to take between S and T, we're going to grab a bunch of vertices. And we just want to make sure that S and T grab something that is the same. Okay? So if we go back, right? So if we go back to what we have proved, so how many things between S and T? How many things did we take? Did Kirsten drop here? All right. So we took, Kirsten said we took at least n-2 objects, or I'm gonna call them I values. Okay. We took n-2 from how many possibilities? Like how many choices along that path did we have?
1 to n-3.
Yep, and so for a total of n-3. Okay, so there's n-3 things in your set, and between the two players, they're going to choose a total of n-2 of them. So what has to be true?
One of them is going to be the same.
One of them has to be the same, right? One of them has to be the same. And so what that tells you is the set S and the set T, there has to be something in common between those two sets. And so what? So we can do exactly what we wanted to do, right? You're always going to have this choice of I. There's always going to be a choice for I out there that you can make. And then you can do this as Eric was calling it, the fish pattern, right? Right. So it's going to look like a fish as you go around, right? So you have the tail of the fish and the head of the fish, right? So that probably maybe 30 minutes ago in some of the groups I was saying, like, that's what we wanted to do in the end of this. We wanted to show that these two sets had a non-empty intersection. Okay, so there's n-3 things that they can choose from, and between the two sets, you're going to have to end up choosing at least n-2, which means one thing has to be the same. At least one thing has to be the same between the two of them. So far, so good? Yeah? All right. So I thought this proof was laid out pretty nicely. It sort of broke it down. What did you all think about this proof style, about the way that it's presented here? You like working through this? So, I mean, the alternative would be, like, I have a few other books over here, like the one that's posted on Plato. I mean, they're just going to lay out sort of the concise, very, condensed proof that is streamlined. This is sort of more, it's broken out a little bit more. And we prefer this style.
Yeah, I prefer this.
Yeah. Okay.
Beautiful.
I feel like I prefer this style because it kind of is forcing me to actually understand what's going on instead of just like looking at an end result and being like, oh yeah, that's it.
Of course, right? Yeah, so that's one of the tragedies of mathematics. I mean, it's one of the beauties, but also the tragedies is, the people who are writing these proofs and figuring these things out, they're spending lots and lots of time thinking about them, refining their ideas. And so as the reader, you're seeing the end result that somebody's worked on for years, right? Maybe. And then, so when you're on the front end of it, they wrote it with years of experience and you have zero experience with that particular work. And so I think this is nice. It kind of breaks it down into how we build things up. All right, so we're 1 minute over. We're out of time here today. But for the weekend, right, the things that are due, we have Hamiltonian homework. Have we been making progress on that? All right, so send that to me. We're not going to do Hamiltonian, so what I'm going to do is I haven't had a chance to scan it in yet, but I'm going to scan in vertex coloring. We're going to move on to coloring next week. And so then we'll hear some presentations about coloring. But give me that Hamiltonian stuff. Weekly reflection, right? So at the end of the weekend, focus on this week. So how is this week different from the previous week? Is it more of the same? You know that we're 2 weeks in now? This is the end of 2 weeks. It's pretty crazy. So end of 2 weeks here. And yeah, so think about that, right? How was the first week? How was the second week? How are things a little bit different? And then email me if you got any questions. So, all right, well, I'm going to call it here, and I'll see you all on Tuesday. Again, I had fun today. Stay safe.
Bye.
Staying healthy. Bye.
Bye.